Homework 7 will be posted Wednesday. And it will be due next Tuesday before your quiz. It will also be 3 or 4 questions. So it will be shorter. And these will be on recitation in part. So recitation Wednesday and Friday will involve looking at things from Homework 7. Finally, Quiz 3 will be on next Tuesday. It will be um, 1 hour long. It will be 2 questions. And one thing that will be unique is, so 1 hour, of course, is not the whole period. There will be a 20-minute discussion beforehand. This discussion will be on the philosophy of science. So what is science? How is science different than things that are not science? So we call this the process of science. And this will be on the quiz. So the things we talk about for the 20 minutes before the quiz will be on the quiz. Will Quiz 3 be on just momentum, or will it be combining everything we learned? So physics tends to build on itself, right? We will see some examples today of problems that combine, or situations that combine, the conservation of momentum with kinematics and with an understanding of forces. If we do the pirate ship problem, that's one of them. We may also do the problem of the stuff that we saw out in the hallway. Does that answer your question, Suryuta? Coconut, we will be having 4 quizzes and a final. Actually, yes, 4 quizzes and a final. Crew 77, yes, you can of course email your TA. If you didn't get comments on Blackboard, then of course email your TA, or you can come to my office hours, which I should probably tell you when they are. Let's see, do we have the whole board in the camera view? I think, yeah, pretty close. So my office hours, when you can come talk to me about anything, are today, as they always are, 1:30 to 3:30 p.m. on Zoom, or room 112 in person. So either way, if you'd like to come chat about literally anything, then come chat. Yes, this is sort of quiz 4, depending on how you count, right? So do we want to count? Do we want to call this one quiz 3 or quiz 4? We can pick whatever naming scheme we want. So by Kay Williams' request, this will be quiz 4. Whatever it is, it's the next one. All right, we'll call it quiz 4. No, we're going to do, yes, we have this quiz, 1 more, and then the final. So there is 1 more after this. There were originally going to be 5. Okay, we'll stick with the syllabus. So this is quiz 4. There's also a quiz 5. So we've got this, and then we've got 1 more. The quiz grades are posted for most people. There are a few that have not been posted. So yeah, if you haven't gotten yours, I don't know what happened. One of the TAs may still be working on it, but I will grade it myself during office hours. If you want to know your grade, come to office hours. I'll grade it myself. Just adjusting the camera here to make things look better. Yes, we drop your lowest quiz. So about the quiz grades, how do you think folks did? Should we collectively pat ourselves on the back? So let's, of course, you won't. So I'd like to ask you all to guess. So in Twitch chat or in Zoom chat, I'd like you to type. We'll do a betting thing. Type what you think the median grade was on the quiz. So remember, so 80 to 100 is an A, 65 to 80 is a B, 55 to 65 is a C, 50 to 55 is a D. So everybody's typing what they think the median was. Everybody's typing a whole bunch of numbers. The median was a 75, which is a B+. And there are a few grading errors that have been brought to my attention that we need to correct, so the median actually may be a little bit higher than that. Typically, the median grade on physics quizzes tends to be a B or a B-. So for the median grade to be a B+, that is significantly above average. So you all are doing quite well. If you are in the batch of folks that you're pleased with the grades you got, then congratulations, right? Go get some ice cream. If you want to do better, remember that we drop your lowest quiz grade, but we also will give you an opportunity to raise some of your low grades later in the class. We will figure out how that works, but that will be during finals week. Some people, so there's like lots of, let me catch up on chat here. Yes, Trapped Dragon, if you got an 85, an 85 is an A. What are people saying? So if your quiz has a grade, but it says it needs grading, I don't know about that. Let me know during office hours, and I'll take a look and see what happened. Some people have said that that they think there is a grading error in their quiz. Boogie1114 says that they think their quiz was graded improperly. If that is the case, if you think there is a grading error in your quiz, contact the TA who graded it, so your grading TA, and say, hey, I think there's something wrong. Here's what I think is wrong. And if you still think, if you two don't agree, then come talk to me. If you so it's with the grading scale, Olive Moose. Yes, the only thing that shows up on your transcript is a letter grade. So I will look at the end of the semester, and if I say, oh, they have a 78, that's a B+. Oh, they have an 85, that's an A-. Oh, they have a 61, that's a C. So the number that you get, right, the number score is I convert that to a letter based on the grading scale in the syllabus, and then that's what winds up on your transcript. Yes, the group quiz grades count. They count 1/3 as much as the main quiz. How do you know who graded your quiz? It was the so Blackboard will say, but it's most likely your grading TA. Yes, the group quiz is graded. If your TA has not done that yet, then poke them and tell them to hurry up. I will tell people to. So Adam, actually, if you could drop a note in Slack right now. Well, I'll do it better. Typing. A lot of students are asking about their group quiz grades. If you haven't graded those, please do that as a high priority. Okay. If you need help doing that, please ask, and we will get more folks on it for you. Okay, so I've just sent something to people. People are grading homeworks as they are able. If your TA is behind grading your homework, then let them know, tell them to hurry up, let me know, and we will get help for them. So we have a procedure in place, basically, if people fall behind in grading, to toss more folks at them. Melmo, you say, okay, Semsquatch, if you have to leave recitation early to go get the vaccine, probably the best thing for you to do would be to go to a different recitation if you're able. But if you need to leave recitation early, you don't need to email anyone. Just go to recitation, stay as long as you can, and then leave to go get your vaccine. Where is the group quiz in the gradebook? So let me look at Blackboard. I have currently a Blackboard tab up. I don't want to spend the whole time today talking about grades, right? I do want to do some actual physics today. So if you have an individual question about your individual grades, please come to office hours. I'm loading. Okay, so here's the thing with the group quizzes. Since there were different ones, there are different columns. Don't ask about group quizzes now, I'm sorry, because of the way we've had to keep track of that. I will get all that sorted out with my folks, and that will be showed in a way that you all can digest. So because of the way we had to do it, it's kind of a mess on our end. If you have a question about your homework grading, R. Martine, please talk to the person grading your homework. If you still have a disagreement with them, then please come talk to me. But in class is not the time to sort that out. When are office hours? Right here, what we just discussed. Kongplash, please email your grading TA and CC me. Individual things, like if I talk to everybody right now about their individual special cases, then we won't do any physics today. So I'm sorry. I would love to help everybody with their unique situations, but unfortunately we need to do some physics. So I want to we've got two big topics today. One of them is kind of some context for the conservation of momentum. Well, I need to write this smaller in the corner. So the first thing is context for conservation of momentum, something called the impulse momentum theorem. So that is the first thing we will talk about. The second thing that I would like to do is your questions from homework or recitation. And then finally, the third thing I would like to do is to talk about examples that involve momentum plus other things, and we'll do some examples. And somewhere in here, Sam is going to come visit, and we will do an experiment. So that is that's what we're going to do. Should you be getting homework back before quizzes so you can have feedback? The TAs will try to get you homework 6 before quiz 4. They may not be able to, but if you have questions, of course, please come to the reviews that they do. Please go to the physics clinic, or please talk to me. The best way for you to get feedback about your homework is to ask. So if there's a thing you're not sure about, ask. I will also see if I have if I can get some time to record some videos for homework 6 and for recitation this week. I'm going to make the beeping thing stop beeping. All right, beeping thing is now not beeping anymore. Kara, we are going to have, we were scheduled to have 5. We combined 2 of them, so we will have 4 with one of them double length. Let's actually talk about physics now and not talk about grades. Yes, there's one more quiz after this one. I'm sorry, I know you all are concerned about your grades, but ultimately just focus on learning physics. Your grades will be fine. So we do need to talk about physics. Sorry. I've mentioned the impulse momentum theorem here. So what is that? Remember how we got here. We said that we started by saying F equals ma, and we observe that acceleration here is the rate of change of velocity. So I could also write this as mass times the rate of change of velocity. So let's kind of write this in words here. Times the rate of change of velocity. Now, mass typically doesn't change. There are a few instances where we do need to think about an object whose mass changes continuously, but usually it doesn't. So what I can do here is put this m inside the derivative sign. I could write force equals the derivative of mv with respect to time. And this is just momentum. Yes, I'm going to do a YouTube update probably today or tomorrow. Last Thursday's didn't get recorded, so you'll have to get that one off of Twitch. So this numerator I can write as dp. So this gives us another way to think of Newton's second law. Force is the rate of change of momentum. And this was actually closer to how Newton originally phrased this. So what does that mean? If I apply a force to an object, that object is going to accelerate, right? If I apply a force to an object, that object's velocity will change. And since momentum is mass times velocity, if the object has a lot of mass, its velocity will only change a little. But if the object has a small mass, its velocity will change a lot. And that idea is encapsulated in momentum. But if I push on an object, then the strength of that force tells me the rate at which the momentum changes. And Christopher says the math to derive useful equations is actually not that difficult. Yes, that's usually true. Often the sorts of mathematics that we use in physics requires careful thinking, but it usually doesn't involve like the horrible sorts of things that show up on calculus exams, because it turns out that the easy calculus, that's often what we do in practice, they don't put on the calculus exams because it's easy. I think they should. So what can we do with this? Well, one way to look at this, so there's a problem that you're going to do tomorrow in recitation where this idea is very useful. You have a problem tomorrow involving a rocket. So a rocket is a machine here that's full of fuel, and a chemical reaction takes place that propels that fuel backwards as gas at high velocity. So we're used to thinking of Newton's third law in terms of forces, but Newton's third law also pertains to momentum, right? Because force is, after all, just the rate of change of momentum. So one way to describe what's going on in the rocket is that the change in momentum of the gas equals the change in momentum of the rocket. And of course, since momentum is a vector, we can make this precise by putting a minus sign there. That's just Newton's third law, but I've written change in momentum rather than force because it's kind of hard for us to think, okay, what's the force on a cloud of gas? So yes, Crew 77, opposite direction there. So this is one expression of Newton's second law. And you will need to do a problem tomorrow where in recitation where you think about Newton's third law in this way. But there's one other thing that is useful for us as well. I'm going to take integrals of both sides of this equation with respect to time. If you're still in Calculus 1, an integral is just the opposite of derivative. It's the area under the curve, the thing that we did for kinematics. So the integral of the force over time, well, if I take an integral of a derivative, that just undoes the derivative and gives me final minus initial. The other thing is that we're only going to think about forces that are constant. So if our force does not change over time, right? So let's make a graph here. If, think way back to what we did in kinematics. If your force does not change over time, what is the area under this curve? So if I have some time t and some force F, how much area is in here? Force times time, yeah. So this was, think way back to the area under the curve stuff that we did. There we were interested in velocity times time or acceleration times time, but here we just have force times time. So if the force is constant, which it will be for us, then, let me keep my colors consistent, F t. So how do I interpret that? So I'll say, I'll write the grammar the other way around this time. The change in an object's momentum is equal to the size of the force acting on the object on it multiplied by the time that force acts. And this kind of seems like a direct consequence of this. If force is the rate of change of momentum, then, well, how much does momentum change? Well, it's however big the force is multiplied by however long that rate of change persists. And that seems like, wait a minute, that's obvious, but that's only because you've thought a lot about rates of change from your previous experience with kinematics. Now, this quantity here, force times time, has the name impulse. And remember, this is really an integral if the force is not constant. So this is really the integral, well, change colors here, really the integral of force over time. So what the impulse momentum theorem says is just this, that over here, change in momentum equals impulse. This is sometimes helpful for us to think about situations, for us to gives us a way to relate forces to momentum, and will be especially helpful in the rocket problem on tomorrow's recitation, where you have to relate the impulse delivered to the rocket to the change in momentum of the gas coming out the back. I want to see if our experiment is ready to go. Oh, timing is perfect. So here's what I would like to do now. Sam is coming by, and we're going to do an experiment for you out in the hallway. So I'm going to put my mask on just for safety. Hey there. Good, great timing. So I'm going to need to move the camera. So what I'm going to do, give me just a minute. I will still be able to talk to you all, and I'll still be able to hear, or still be able to read chat. So this box needs to come over here. And then, does Sam like green eggs and ham, Sam?
It's been banned.
Not green eggs and ham. It's the other Dr. Seuss books that had.
Oh, that's not on the banned list?
No. All right. So you all are going to lose video for a minute because we're now running the camera off of batteries, and I'm going to have to pull out the power cable and put a battery in. So, yep, that's fine, Sam.
You got enough room?
Yeah, we're good. So we're going to pop this battery back in here. So you're now on TV, Sam. Let's make sure that so you're now seeing the hallways in the physics building. Now what I'm going to do is adjust something here so they can hear you. Sam, they say you have skater pants.
What's that?
They say you have skater pants.
No, they're hiking pants.
He says they're hiking pants.
Okay, so Sam, can you say something and
My pants unzip here to turn them into shorts when the day starts cold and gets warm. Check 1, 2. You good?
they've asked you to check your zipper.
It's a belt. My zipper is just fine.
So you now can take this headset off. And we're now on the mic on
The camera.
the camera.
Excellent.
Let's scoot this stuff back like a couple feet. So I have chat here on my
Okay.
phone,
Mhm.
so I can read what they're saying. Okay. So
Ugh. I'm too old for this.
here we are.
You have to be careful.
I
You
have
should-
to be careful.
you
Yes.
should come
So,
this way.
so I've got here a pretty heavy ball. How much does this weigh, Sam?
I think it's 40 pounds.
This is not 40 pounds. I'm
No,
not that
20
strong.
pounds. 25
20
pounds. 20, 25 pounds.
So if I throw this to Sam, what's going to happen?
I'm going to throw up.
He's going to throw up. No. If I throw this at Sam, what happens? I will go backwards. He catches it, and what will happen to him?
Nothing, because I'm just catching the ball.
Yeah, so Sam's just catching the ball. So they say I'm going to go backwards. But you just sit there?
Sure.
Okay.
Because I'm just catching it.
You're just catching it, so let's see what happens.
Oh, I went backwards.
So
So did you.
both of us have started to move. So now, throw it to me real hard. Same thing. So here's a question for you all. Whoops, I have back. I lost chat. Sam is on, yeah, he's also on a little wheelie thing. No, we're not throwing the phone. What affects how far each one of us moved? We need some backup sensors, yeah. What affects how far each one of us moved, folks? How hard we throw it. Okay, so let me,
Anything else?
yeah, what else? The weight of the ball, yeah, so the mass of the ball, how hard we throw it. What else affects how far we go? Our individual masses, yeah. So the air resistance of my hair is one of the answers. And so Agnes Schultz says friction.
But technically that affects how far we go. Yes.
Yep, yep. So let's, how much I lift. So let's see. Let's kind of make a measurement. So let's put these two cars right next to each other. Right?
Okay.
Now let's give it a little more room. So we're one thingy apart.
One floor tile apart.
One floor tile apart. So I'll throw you the ball.
Okay.
We'll see how far each one of us skids, and then we can figure out something about the coefficient of friction.
Okay. I'm at this floor tile right here.
You're at that one? I'm on this one. Here we go.
What about one floor tile?
So Sam went one tile, and I went
You went about 2, I think.
two, or no, I went three if I was up there. Or 2.5.
We didn't start at the same floor tile. We started one apart.
Yeah, yeah. So let's do it again.
Yeah, you went 3.
Yeah, let's do it again. So,
Okay, so I'll start here again.
yeah, so you throw it to me this time.
Okay. I hardly went, which you went.
I went three.
1, 2, 3 floor tiles.
Yeah, so why is the ball so big?
It's a medicine.
The ball is really big. Yeah, it's a medicine ball, and it's called a medicine ball because you get exercise throwing it around.
Ask if they heard of Jack LaLanne.
Heard of, well, you ask them.
Have you ever heard of Jack LaLanne? This is like a Jack LaLanne era vintage medicine ball.
It's mostly made out of tape
And leather.
and leather. So Lumbo has said, am I twice the weight of you? So I am pudgy, but
This cart has much more friction.
yeah. So if I'm the one who's has higher mass, would I move further or not as far? Turn around and look at everybody. Yeah. So if I'm lighter, I would go further. But if this has less friction, it would go further. So folks, what kind of experiment could we do to figure out if it's that I'm lighter or if this one has less friction? So a student suggests we could switch cards.
That's an excellent idea.
So let's do that.
Okay, do you want to just switch positions or switch cards?
Let's just do this. And now you can see what they're up to. So. That's the camera.
Oh,
That's what they're saying.
Oh.
So that's the broadcast.
oh, this is delayed.
It's
way delayed.
It's delayed by about 2 seconds.
Okay.
So
Okay, so again, we're about 1 floor tile apart. We should go that way. Another one.
should go this way another one. Yeah.
Because I started there. And
Yep.
You were about here,
All
correct?
right.
Okay.
Here we go. many did you go?
1, 2, 3, 4 floor tiles.
So Sam went 4.
So let's come back to our starting
Yeah.
places. No, you got to back up one.
So actually, let's turn it sideways so they can, now that we know how far we're going to go. So I will, why don't you come over there?
Oh, go that way?
Yeah. That'll be cool. Folks, we usually do this in the auditorium. Yeah, here we go. All right, so
See ya.
yeah, so I went about 1 tile's worth, and Sam, how many did you go?
About 3.
About 3. Okay.
Okay. Hey, Livium.
So
Okay, you good?
yeah, we're good.
Okay, you want these out of here or leave them here? Up to you.
You can take them back to the basement.
Okay. All right, later.
Now, oh, we have some questions. So what do the students ask? So one of them says, red cart be less frictiony. 2 grown men playing catch on skateboards.
Yep.
Ah, we have a good point. Maybe the hallway isn't level.
That could be, but I've done other things in this hallway and it's pretty level. So,
Okay, so somebody, Gislo has a really good point,
okay.
who says, is this impulse like super short since time is super small when throwing the ball? Yeah. So the impulse is force times time, right? So in these cases, like me catching the ball takes what, like 1/10 of a second? Which means the force has to be big and the time small. This is why we can ignore other forces. We can ignore friction at the moment of collision, right? Because, yeah, there's friction. You saw that. The carts come to a stop. But they don't come to a stop at 1/10 of a second. So at the moment of throwing and catching, friction doesn't matter.
Static friction is small compared to the force that's applied to us, right?
Yeah, okay. Somebody else has said, so a student has said, we throw with different force. Sam is a lot stronger than me. So does it matter? What would happen if I throw not very fast and Sam, because he's stronger than me, throws the ball really hard? What do you all think will happen?
Walter will throw up.
I will throw up. So if Sam throws the ball harder, which one of us will move further?
Or do you not have enough information?
Yeah, maybe you don't. So somebody says, does posture matter? So they're saying both of us, Slimeballs 24 is their name, says it'll be proportional, right? So if Sam throws the ball harder, we both go further. Yeah, we could do this again with Sam like whacking it over his head and thumping me with it as hard as he could. Yeah. So the idea, right, so think about this now in terms of conservation of momentum. Sam gives some impulse to the ball. Right?
Correct.
Now, how is your momentum going to change when you throw the ball?
Does it depend on how I throw it?
Just, you mean like whether you throw it slow or fast or whatever?
No, whether I throw it straight at you or straight up in the air.
Oh, that's a good question.
I think that's what the one student was
Oh,
alluding to
about
before.
posture.
So I could throw the ball really hard and only give it a very tiny momentum in that direction.
Yes. Right, so if Sam throws it up in the air, Sam's not going to move up or down because there's a floor here, right? So, yeah, this is an illustration of how X and Y components of things are separate. Yeah, as Porpoise says, momentum has a direction. So this we kind of have a disagreement. Some people are saying I would move further, and some people are saying both of us will move further if we throw it harder. Do we want to do another experiment, or do you?
Can they justify that?
Yeah.
What's
so
the justification for that?
right. So justify how if Sam throws the ball harder, maybe he will move further, maybe I will move further, maybe both will move further. So what's the physics or the justification behind that?
Sure, let's just do a quick
Yeah,
experiment.
let's just do it.
We don't need two parts for this one, so let me see the ball.
Yeah,
Okay.
there you go.
Okay. I'm just gonna throw the ball in my wimpy little way. What did I move?
Like half a
Tile? Okay. So I'll come back here. Thank you. And now I'll throw it hard.
All right.
Start right here.
You notice he threw it hard enough that it kind of knocked me backwards a bit.
4.5 tiles.
Mm-hmm. Yeah, so momentum is conserved both for the throwing person and the catching person.
Okay, so now we know that if I throw it harder, I go back farther. What happens to Walter when he catches a harder throw? Or Professor Freeman? Who are you in this class?
I'm Walter.
Walter, okay.
It's good enough for my parents, it's good enough for my students. So now you want me to sit there and you throw it at me?
If you want to try that, sure. This will be fun.
Sure. Let's turn it around. So looking at the camera here. Yeah, so
I'll try and stay out of the way. Okay, so the first one's going to be easy throw.
all right.
Okay.
You threw it pretty hard.
I didn't think I did. Maybe the floor is slow.
The floor isn't flat.
So you want about 6.
Yeah. So now go ahead and really throw it at me. See you later.
Actually went a lot farther.
Yeah.
Yeah, cool.
So
Yeah, no, I don't think the floor is sloped. I just think it was more of a horizontal
yeah.
throw.
So the response is, damn, he really let that rip. So Dinara has written that the force on Sam equals minus the force on Walter. And I mentioned there are vector signs that we can't type here. So yeah, force is equal and opposite. But based on the math we just did, since impulse is force times time, the impulse has to be equal and opposite too. Right? That's really the thing, because whatever momentum you give to the ball then gives to me.
Correct.
When I catch it. So somebody has said, Sam throwing while stationary on the ground made me move more.
Okay, ask for a justification for that
Yeah,
one.
so why is that? Because of more friction on you, they're saying?
But did I have any direct interaction with Walter? Me, myself. Did I have any direct interaction with Walter?
I don't know. All I know is somebody threw a ball at me.
Right? As far as you care, all you interacted with was with a ball. You only interacted with a ball.
So now Sam Squatch has said, yeah, the thing that changes is the velocity of the ball because you can throw it harder when you're standing up rather than sitting on the car.
Valid point. I'll buy that.
Because that almost like knocked me back off of this thing.
Yeah. So, valid point.
Yeah, there we go. Yeah, we have a lot of students who live inside that lens. So thank you so much for doing this experiment with us.
I had fun. It was a good time.
So what would happen if we threw something really hard? What would happen on this card? Suppose I didn't have one of these. Suppose I had like a whole barrel full of these balls and I just kept beating them off of here. What would happen?
You're asking me?
Yeah, or them. What if I had
I'd
like
rather ask them, yeah.
100 of these and I just kept throwing them? I would keep moving backwards. Would I keep moving backwards at the same speed, or would something change? I'd move backwards with increasing speed, yeah. Why? They say I would accelerate backwards. So why would I accelerate backwards? They're using the word acceleration now, so why would I accelerate? Okay, so some people are saying different speed because the mass is different. But how is that different if I just took the balls and set them on the ground? I build the speed because I continue to throw. There's no other force going against the throws. Yeah. So Slimeballs 24 has it that as I throw the ball, I have to push on it, right? And it pushes back on me. So if I have a lot of things to push on, right? So if I think about moving my cart, I could just like reach down and push on the ground.
Yeah.
But if I don't have any ground to push on and I instead push on a supply of big leather balls that I brought with me, would that work too? So Trollo XXX24 says, would the increase in distance between where the ball is thrown from me make a difference? Not so much, because we wrote a bunch of equations on the board with conservation of momentum. They don't really care about where you are, right?
Is there x in any of those equations? I don't think so. No, I see no x.
So if I had, suppose I want to go really fast, and I have a supply of these leather balls, what would I do with them? Oh, and Porpoise has got it. This whole thing is a metaphor for rocketry.
Yeah.
Yeah. So do we have a machine that like throws leather balls really, really fast, Sam?
I don't. Do I?
What about little ping pong balls?
Oh, I have one that throws little ping pong balls really fast.
Anything smaller than little ping pong balls? Like atoms?
I don't have one.
You don't have a machine that shoots atoms?
I don't.
I thought you did. Big fire extinguisher? Shoots atoms at the back?
Oh, okay. Yeah, I'll buy that. Yeah. Okay. I forgot about that.
So we actually have a rocket down in the basement, which we might demonstrate for you at some point.
You want to do it Thursday?
Let's do it Thursday.
Okay.
So on Thursday, we're going to do a demonstration, not of big leather balls, but of lots of tiny balls that we call atoms. So we actually have a rocket down in the basement that will fly around the hall for you. Thank you so much, Sam, for
That was fun.
doing this with us.
Tell them to have fun in lab this week doing impulse and momentum.
Yeah, Sam says have fun with impulse momentum.
Are they? Yeah, I just said it on the ground. All right. Are they saying they hate lab now?
I don't know, are you saying you hate lab?
I hate lab.
Oh, you can do a balloon attached. Oh, so somebody wants us to do a balloon, like full of air, and make it squirt the air out the back.
We could do that too.
You could do that too.
Okay.
Oh, and
Later.
someone also mentioned the supersonic ping pong ball cannon. Oh yeah, that's right. We do
How
have.
do I know about that?
I don't know. Well, apparently there's a YouTube video, not of ours, but of someone else's.
Oh, okay.
So yeah, we might use air pressure to blow something up later too.
Okay. Later, y'all.
See ya. All right, so there was our little experiment. We've got 20 minutes left. Let me just get the camera back where it goes and let me get it aimed back at the blackboard. We have time for to talk about some examples. We can either use an example that I generate here, or we can use one of your recitation problems as an example. Which would you rather do? Would you rather talk about recitation problems from last week, or homework problems? Or would you like to do a totally new example you haven't seen yet? All right, let me switch the mic back over to my headphones so you can hear better. You want to do, so we have new example, homework.
Okay. On the new mic now. Some people say, Aki507 says that they want to do the last recitation problem from last week. Sajad says recitation problems. And so folks who were typing on Zoom, I'm sorry, I wasn't able to have Zoom on my phone, so I was only able to respond to Twitch chat when I was out in the hall. Now I can see both. So, okay, lots of people are saying the recitation problems. So which recitation problem from last week do you want to address? This may be our example here. I kind of really want to do the one with the cars. So we'll do that one. I guess I can say I'm the prof, I pick what we do. So here is the situation. We have some roads. Let me make sure that I draw things just as I gave them to you. Recitation problems from last week. Okay, so this is problem number 4 from recitation last Friday. So there is a Mini Cooper, which we'll call car A. It's going that way at 10 meters per second. And there was a Toyota Camry going north at 15 meters per second, which we'll call B. The Mini Cooper, being smaller, had a mass of 1,200 kilograms. The Camry had a mass of 2,000 kilograms. So these two cars collide in the middle of the intersection. And since it's a collision, they stick together. So let's draw the intersection again. So draw them, I suppose, like this. And then the cars have smushed together. Which direction do you expect them to move after the collision? I'm just getting my the window back up that I need to see what you all are saying. There it is. Up and left, yeah. So you expect after the collision them to be going this way, and we'll say this is V. I'll call this V2. We'll see why in a moment. So after this happens, so this is cartoon number 1. This is cartoon number 2. And after they collide, they're moving that way. So what's going to happen after the collision? They collide, they stick together, then what? Yeah, and Itzmaz has said northwest. Beckmunch has said more up than left. How do you know it's more up than left? You're right. Yeah, northwest if you want to be picky. Yeah, it might be more this way. Right. We'll calculate that. They're almost going to hit me standing on the corner. That is exactly what happened. In this is a real situation. When I was working on my PhD, I was walking to work, minding my own business at the intersection of 10th and Highland, no, 11th and Highland in Tucson. I was standing right here on the sidewalk where the people go. And these two cars collided, and they came flying at me, and I had to dive out of the way. So this is a true story. D. Maxter has said the Camry's momentum is greater than that of the Mini Cooper. Yeah, it's going faster. Because this person has the right of way, and this person just like the Mini Cooper didn't stop. So yeah, the magnitude of this momentum is bigger than the magnitude of that momentum. So it's going to be more up than left. So the last part of this question asks us to figure out how far these two cars slide before they come to stop. It's not that I'm too strong to die, it's that I got the heck out of the way. And I called 911. The driver of the Camry was hurt a little bit, but it turned out she was just burned by the coffee that she was drinking that spilled all over her. It was very hot. So everyone was okay except for the cars. So it's a story that ends well, which is why we made a physics problem about it. So these two cars now have smooshed together, and they have moved some distance over here, where they're now smooshed together in a heap over on the sidewalk. And they're not moving at this point. So this problem involves a collision. It also involves something else. So we have we need some way to understand how to get from this picture to this picture and how to get from this picture to this picture to understand how things move. So what technique, what physics idea can I use to relate picture 1 to picture 2? Yeah, Michael, exactly, as you said in Zoom chat. Vector addition. Yeah, so we're going to do some vector addition. That's going to be involved in us doing this. Porpoise has written an equation, but what technique do we use? Like, what principle does that equation represent? Conservation of momentum, yes. And how do you know that conservation of momentum was the right thing to do here? There's something happening in this situation that signals that conservation of momentum is an appropriate approach. So some of you are using the terms inelastic collision. So let's write this down. So we haven't used that term because it's actually not, it's just kind of a vocabulary word. All inelastic means is that the things stick together. But what really matters is that it's a collision. Yes, as Crew 77 says, conservation of momentum holds for any collision. So we know conservation of momentum is appropriate here because it's a collision. So we know how to get from picture 1 to picture 2. So this is the conservation of momentum. But what technique can we use to get from picture 2 to picture 3? Yes, so Not So Great Britain has said the fact that it is inelastic means they share a final velocity. Yes, they stick together, so they both are going to have the same velocity v2 after the collision, exactly. So what do I write by this arrow? How do I get from this cartoon to that cartoon? So vectors perhaps, but I need, rather than a math idea, I need a physics idea. People are talking about equations. So Crew 77 has said that mass 1 times the sum of their velocities equals mass 2 times the velocity final. They don't have the same mass. Yes, Porpoise, as you've written, each of them has a different mass and a different velocity in the beginning. But at the end, right, this term Vf times m1 plus m2, both masses are moving at the same velocity. And of course, there should be vector signs over all those v's. But Michael Kelly, meanwhile, in Zoom chat, has said that here we should use kinematics. And why is that? Well, here we have motion. We need to relate distance, acceleration, and change in the velocity. And we can find the acceleration from Newton's second law. So I've got 8 minutes left. Let's actually do this. So we have now 2 steps. We're going to use conservation of momentum to find v2, the velocity after the collision. And then we're going to use kinematics to figure out how far that velocity would make me slide. So I got to erase the board for us to do that. This idea that you're seeing here, that you had in recitation on Friday, is something that we will see again and again and again. And this is important. Problems where, in one step, conservation of momentum lets me make progress, but in another step, in what happens next or what happens before, I need to use something else. So picture 1 to picture 2, we're going to use conservation of momentum to find velocity vector 2, and then step 2 to step 3, we're going to use kinematics to find the distance. So let's just do those things one at a time. So I know that momentum is a vector, right? So that means in both x and in y, I know So these things are going to have a lot of subscripts. Conservation of momentum in x. So this is the, initial velocity in x of car number 1. I called them A and B. We should do that. So that's going to be A, B, B. And then after the collision, both of them are moving together. They share a velocity m, v2x. Because we labeled v2x as the velocity after the collision. And then in y, ma v a y initial plus mb vb y initial equals this, v2y. Now, some of these things are 0. Right? We know that the Camry was driving north, the Mini Cooper was driving west. So what did we have? I think I labeled this one as A and that one as B. Right? So car A has an X component but no Y component. So that goes away. Car B has a Y component but no X component. So that goes away. So what I wind up with is, let's see. I'll get this out of the way. We have v2x equals, so it's just going to be this divided by that. So VAX initial times this ratio of masses, MA over MA plus MB. Likewise, V2Y equals VB Y initial times MB over MA plus MB. So this is the velocity right after the collision. And you can calculate how big it is. So I am spelling out a lot of in-between steps. But yeah, if after class you want to talk to me about what you did, then I can, chat you through that. But now, so now we have figured out the velocity after the collision. So for the interests of time, I'm not going to do the numbers. It's not a straight arrow. But you have something like this. So this is the V2 vector. V2x, V2y that we find. Why is VA not... You're asking about this, Bakupai? A little bit. I'm trying to understand the reference. So we have 1 minute left. I will maybe run 30 seconds over in explaining this. So the second bit So real quick, we know the sum of the forces in the x direction equals max. Force in the x direction is going to be kinetic friction as it slides. So I know mu times ma plus mb g. So the normal force is mg equals max, and that's in the opposite direction. So, just ma. No, what am I doing? Ma plus mb times acceleration. That cancels. So I get an acceleration of minus mu g as the cars slow down. And then I can just use kinematics to figure out how far it goes. So please indulge me for 30 seconds if you don't mind. We have this kinematics equation. That lets me relate the velocity of something, the initial and final velocities, to the acceleration and how far it goes. We derived that a while back. So here, I know that I'm coming to rest. This, whoops, crossed out the wrong one. I know I'm coming to rest. So this is just v2, because the starting velocity in the sliding is the final velocity after the collision. And I can use this relation to figure out the distance that I slide. We can talk about this more on Thursday. I know that I ran out of time just a bit at the end of this. I will hang around and answer anybody's questions, but I know I need to let everybody go because it's 12:20. Thank you for your indulgence here. And we'll have more time for questions on Thursday before we start our new topic. We've just got one topic for Thursday that'll require us to learn like 2 more things. So thank you all. I'm sorry the timing was a little bit squirrely today, but that's okay. We'll pick up on Thursday. I will hang around and answer anybody's questions if you have them. I'm going to stop the recording and upload it to YouTube right now, and I need to get the video library. And I know people have, we never did do solutions for homeworks 2 and 4. I just ran out of time to record things. I guess we could go back and do that if I get time, but you'd probably rather see the newer homework sets.